Today, we want to talk about the next big thing, which is solving oblique triangles. An oblique triangle is just a non-right triangle. So the game that we're going to play is the same as when we were playing the solve right triangles game. There are 6 things about a triangle, 3 sides and 3 angles. The solving triangles game is given 3 things, find the other 3. The difference now is that you're not given a right triangle. You're not given one of the angles to start. You're not given a right angle to start. In the solving right triangles game, it was still given 3, find the other 3, but one of the 3 things that you were given was a 90-degree angle. So now we're just going to play the evolution of that game where you don't have a right angle. The game is still the same. Of the 3 sides and 3 angles, I have to give you 3 pieces of information, and you have to find the other 3. To streamline the process, we're going to have what I call the usual triangle, where the things opposite match. Side A is going to be opposite angle alpha or angle capital A. Side B will be opposite angle beta, or we'll call angle beta angle capital B. And side C will be opposite gamma, or angle capital C. So we'll use capital letters for the angles and lowercase letters for the sides. This will happen when I get tired of putting in alpha, beta, and gamma when I'm typing up quizzes. I go, ugh, this is such a pain, and I'll just use capital A for instead of alpha. It's also common to use capital letters for the angles and lowercase letters for the sides. I'm not really a fan of using capital letters for the angles, but I'm not really sure why. I have a feeling that some pre-calculus or trigonometry instructor in my past has turned me against using the capital letters. But when I think back to geometry, that's how we use capital letters to refer to the vertices of a figure. So I'm not sure where it comes from. So I'm trying to include it back in my teaching now, 30 years later. All right. Let's talk about the tools that we have and also the tools that we don't have. Most of the tools that we had for solving right triangles were dependent upon the right triangle part. So sine is opposite over hypotenuse requires that we have a hypotenuse, which means we need to have a right triangle. If we don't have a right angle, we don't have a hypotenuse, we can't say sine theta is opposite over hypotenuse. Also, we use the Pythagorean Theorem, which said the sum of the squares of the legs of a right triangle is equal to the square of a hypotenuse. Once again, right triangle and hypotenuse, a thing that we do not have anymore. The sum of the angles is still 180 degrees. So we need to talk about the tools that we're going to use. So the sum of the angles in any triangle is 180 degrees. We still have that. So alpha plus beta plus gamma is 180. Or using the capital letter thing, A plus B, capital A plus capital B plus capital C is 180 degrees. So the protocol that we had before, where as soon as we have 2 angles, we subtract to find the third, that's still in play. As soon as you have 2 angles, subtract to find the third. That is still a thing that we're going to do. That's still part of our strategy. As soon, not as soos. As soon as we know two angles, we should subtract to find the third. Go after the easy stuff first before you go after the difficult stuff. But we're going to need a new set of tools. The other tools that we have, the Pythagorean Theorem and the right triangle trigonometry definitions, those are off the table because they require a right triangle and a hypotenuse. So we need some more tools. My favorite tool to introduce next is called the Law of Cosines. Now, I know most of the other trigonometry instructors are like, "Oh, dude, what are you doing? You're supposed to start with the law of sines. It's easier to implement." And my response is incorrect. It is not easier to implement. It's way worse than the law of sines. I only am guessing at that because most of the books do law of sines first, and I don't know why. Here's why I like the law of cosines. The law of cosines is like the generalized form of the Pythagorean theorem. It's the Pythagorean theorem for non-right triangles. I'm going to put that in quotes because that's a fishy thing to say, but it's the Pythagorean theorem for oblique triangles. It's the generalized Pythagorean theorem. I don't know why the D is trying to run away here. So law of cosines is a generalized Pythagorean theorem. I just saw the auto captioning. The law of cosines is the generalized Pythagorean theorem. No, it doesn't know what Pythagorean is. So in our usual triangle, where angle side A is opposite angle alpha, side B is opposite angle beta, side C is opposite angle gamma, the law of cosine says the following. C squared is equal to A squared plus B squared dramatic pause because you're like, oh, wait, isn't that the Pythagorean theorem? But then we have this Raiders of the Lost Ark moment where we only have, that's only one side of it, minus 2AB cosine gamma. So it's like the Pythagorean theorem with this extra term, minus 2ab cosine of gamma. Here's some cool stuff. Note that if gamma is equal to 90 degrees, then C is the hypotenuse, and cosine of gamma is equal to 0. And we end up with C squared is equal to A squared plus B squared, which is the Pythagorean theorem. So note, if gamma is equal to 90 degrees, then cosine gamma is 0, and C is the hypotenuse. So it's the Pythagorean theorem for oblique triangles. We need that the extra term of minus 2ab cosine gamma. But C is not the only thing that could be the hypotenuse, because gamma is not the only angle that could be 90 degrees. Alpha and beta could also be 90 degrees. So we're going to have two more versions of this law, two more versions. There's the C squared is equal to A squared plus B squared minus 2AB cosine gamma. Notice that the ones on the outside are the matched sets. C and gamma is what's related here. So we can also write B squared is A squared plus C squared minus 2AC cosine beta. The outside ones, B and cosine beta, those are the ones that the match set. And then we have the alternate sides in the middle. But there is another. I can also have the A squared be all alone. And in that case, we'll have B squared plus C squared minus 2BC cosine alpha. So we got three versions of the law of cosines. The one that we use will depend on what angle we know. So we got three versions, and the version that we'll use will depend on the angle that we know or the side that we're looking for. So we'll use C squared equals A squared plus B squared minus 2AB cosine gamma if we happen to know gamma and we want to find C, or if we know C and we want to find gamma. So the one to use depends on what you're looking for at that moment. So the version to use depends on what you're looking for. Now, you don't have to sit down and memorize these three equations, but you do have to remember them. If that means that you're going to have to sit down and memorize them, then so be it. Better would be just to do so many problems that you become incapable of forgetting them. So let's do an example. So remember, we've got C squared is A squared plus B squared minus 2AB cosine gamma. B squared is A squared plus C squared minus 2AC cosine beta. A squared is b squared plus c squared minus 2bc cosine alpha. There's our law of cosines. So how we're going to play the game is the game is going to be the same that we played with solving right triangles, although we won't have a right angle. And we'll also have the wrong book open up. I was about to just have to immediately switch to calculus because that's the book that I had opened up on my other screen. Let's suppose that we have side A is equal to 15.3 centimeters. Side B is equal to 8.4 centimeters. And angle gamma is equal to 37 degrees. So what we want to notice is the kind of information that we're given. Let's draw our triangle over here again. Where we have angle alpha, opposite side A, angle beta, opposite side B, and angle gamma, opposite side C. So what we have in this scenario is A, B, and gamma. Side A, side B, and gamma. We have two sides and the angle included in those sides. So this set of information is two sides and the included angle. Because I have side A, side B, and angle gamma is the angle that's included in sides A and B. Two sides and the included angle. We refer to this case as the SAS case. SAS for side, angle, side. Because we have a side, we have an angle, and a side. If instead of side B, I had side C, I had a set of opposite information, that would not be side angle side because it would be two sides and an unincluded angle. That would be side side angle case. We don't want to start with angle. So this is two sides and the angle between those sides. So we write it SAS. So two sides and the included angle. When we're given two sides and the included angle, this looks like a job for the law of cosines. Because look how well this information is going to fit in to find side C. I can use these two sides and the included angle to find side C using this first version of the law of cosines because it involves gamma. So we're going to use the first line. We're going to use the first line from the law of cosines Because we have angle gamma. So we just plug in A, B, and gamma. And we're also going to take a square root. So I'm just going to take care of this all at once. C is going to be the square roots of A squared plus B squared. So A squared is 15.3 squared plus B, 8.4 squared, minus 2A B times a cosine of 37. Now we're just in the land of the calculator exercise. And I'm just going to type it like I write it. Square root of 15.3 squared plus 8.4 squared minus 2 times 15.3 times 8.4 times the cosine of 37 before I hit enter. Make sure I'm in degrees. Okay, I'm in degrees. So I got 15.3 squared plus 8.4 squared minus 2 times 15.3 times 8.4 times the cosine of 37. Close the cosine, close the radical, hit enter. And apparently side C is 9.97. We didn't really have a choice in what we went after first. We had to go after side C first, because that's what the information we were given forced upon us. Because we had two sides and the included angle. So we went after the next side using the law of cosines. We don't want to memorize a case and attach that to the sign, to the law that we use. We just want to know what the laws are and then see how we can use those laws based on the information that we're given. It's better than trying to memorize on top of everything else that we have to remember. SAS case means law of cosines. Go after the side that you don't have. At this point, we have an abundance of information. We now have 4 pieces of information. So we can use what we want to go after the rest of the information. Unfortunately for our heroes, I have not seen fit to give you the law of sines, so we're going to have to use the law of cosines again, which means we're going to have to use this piece of information, and it has been rounded, so we're going to have to be careful and make sure that we use all of those digits. Now, at this point, a great thing happens. We have a choice about whether we go for alpha or beta next, but also a terrible thing happens. We have a choice about whether to go for alpha or beta next. And so we have to make a choice, and that's the bad part. So notice that we have we can go after alpha or beta because I now have A, B, and C. So I can go for beta if I use beta. B squared is A squared plus C squared minus 2AC cosine of beta. Or since I have A, B, and C, I could use line 3. A squared is equal to B squared plus C squared minus 2BC cosine alpha. I'm going to go, we have a choice. We can choose to find beta with line 2 or alpha with line 3. Because each line of the law of cosines has 4 holes in it: A, B, C, and alpha, or B, A, C, and beta, or C, A, B, and gamma. So we have to know 3 to find the fourth. Also notice that it's really easy to solve, say, line 2 for B, but we're going to have to do a little bit more work to solve for beta. So if we have B squared is A squared plus C squared minus 2AC cosine beta, we're going to have to rearrange this a little bit to figure out what beta is in terms of the other 3. So I'm going to have to subtract the A squared and the C squared. So B squared minus A squared minus C squared is minus, spelled minus wrong, minus 2AC cosine beta. I'm still trying to solve for beta, so I'm going to have to divide by the minus 2AC. So B squared minus A squared minus C squared all over minus 2AC equals cosine beta. And now we can apply the cosine inverse. So beta is cosine inverse. I don't like dividing by this negative 2AC. So what we're going to do is multiply everything in this fraction by negative 1. So I'm going to say positive 2AC minus B squared plus A squared plus C squared. That's why when we see beta solved for in the law of cosines, we see A squared plus C squared minus B squared over 2AC. So there's the second line of the law of cosines, solve for beta rather than B squared. Beta is the cosine inverse of the numerator is A squared plus C squared minus B squared. So 15.3 squared plus C squared. $9.97. I'm going to write that in an alternate color because so 9 because it's rounded off. And I don't want to use rounded information. Minus B squared. Let's see, all this is in the numerator. So I want to make sure that the numerator is in its own set of parentheses. Then we'll divide by 2 times A times C. C has been rounded off, so I'm going to make sure I kind of. Now notice that there are operations in my denominator as well. So I'm going to want to put parentheses around the denominator. And then finally, I can close the cosine inverse. So notice I have the numerator in parentheses. And I have the denominator in parentheses as well. Also note that I have my rounded off information, the 9.97. I don't want to use 9.97. I want to use all these digits. So I'm going to press second answer because that way I don't have to type all those digits, but I get to use all those digits. So let's type it in. We want the cosine inverse, second cosine of the numerator parentheses, 15.3 squared plus 9.97. So I'll press second answer squared minus the 8.4 squared. That's the numerator. Divide by the denominator, which is in parentheses 2 times 15.3 times the 9.97. I don't want to type 9.97. So I'm going to press second answer because my calculator right now has a 9.968386454 button on it. Then I'll close the denominator and close the cosine inverse. Double check. 15.3 is a squared plus c squared minus b squared divided by 2 times a times c. And this is all being cosine inversed. So it looks like angle beta is 30.5. Now we could use the third line of the law of cosines to find angle alpha, but at this point, we know 2 of the angles, so we should subtract to find the third angle. Now we know 2 angles, so we subtract to find the third angle. That's our old protocol from before. So angle alpha is 180 minus the original, minus the 37 degrees. I don't know why that's original. Minus the 30.5 degrees. So 180 minus 37 minus the one that I just found. 112.5. Any questions? Now keep in mind, solving for beta, that was a choice that we made. I had to pick solving for beta or solving for alpha. But we could have, and that at that point, solved for alpha. So beta is cosine inverse of a squared plus c squared minus b squared over 2ac. We could also have solved for alpha. So alpha at this point would look like cosine inverse. And I'm just going to follow this pattern. Instead of a squared plus c squared minus b squared, beta and the negative squared one are, that's the matched set. So I'll have b squared plus c squared minus a squared over 2bc, and then find the cosine inverse of that. So in Marvel's what if category, now what that means is that, let's see, let me get my 9.97 button back. So I could solve for alpha by doing the cosine inverse of the numerator, b squared plus c squared, that's the 9.97, minus a squared. Close the numerator divided by open the denominator, 2 times b times c. Close the denominator, close the cosine inverse, and hope that it comes out to 112.5, which it does. And then at that point, since we know two angles, we subtract to find the third. So 180 minus 37 minus the one we just found is the 30.5. So it's good to see that it didn't matter which we chose to solve for, alpha or beta. But that's going to highlight the fact that at that point, we had to make a choice. We had to pick one to solve for. Any questions?
Is there something special about what we're doing here that using rounded values would introduce unacceptable inaccuracy?
Using rounded values could introduce error. In this case, it's not going to be a lot of error, but I'm trying to build good habits and use rounded off information as little as possible. So let's actually see that it's not that different. 8.4 squared plus 9.97 squared minus 15.3 squared. Close the numerator, divided by, open the denominator, 2 times 8.4 times 9.97. Here, close the denominator, close the cosine. Here I've used 9.97. I've rounded to the nearest hundredth instead of the nearest all these digits. Oops. And I have, oops, I forgot to open up the numerator. And it would still be rounded off to 112.5. I've lost some of my calculations. There's the 9.97. So as we can see, 9.97, we still get the same 112.5. We're not off until we get to the nearest hundredth at 112.51 versus 112.53. So we got 527 versus 511. So we're only off by 16 thousandths. And as usual, if the more rounded we get, the further off our answers are going to be. So if we trade our 9.97, I could use that one. Trade our 9.97 for 10.0 because we rounded the nearest 10th. Now we're off in the 10th spot, 112.2 rather than the 112.5. Honestly, I would have to be in a really foul mood to be like, oh, you put 112.2 because you rounded it off. Well, that's minus 1,000,000 points for you. But since I'm letting you do the quizzes over again, I might just be that petty. I don't know. We'll have to see. Like if it's a day that I ran out of coffee and I'm coming up with scores, then I might call, nah, do it over again. Any questions? Let's take a look at another scenario where we can use the law of cosines. Let's suppose that A is equal to $894. B is equal to 850. And C is equal to 810. Oops. I like these numbers. These are the nautical miles at the three corners of the, I think these are the three corners of the Bermuda Triangles where they got these. So it's totally appropriate that it was just like missing. All right, so in this case, our given information is all three sides. So we call this SSS case. This is another job for the law of cosines. At this point, we can choose any form of the law of cosines to solve for any of the angles first. So we can choose any of the law of cosines to find our first angle. We can go after alpha or beta or gamma first, our choice. So good news, we can choose. Bad news, we have to choose. I'm going to choose to find gamma first because that's the only one that I haven't written down. And this will give us practice writing that down. So gamma we're going to follow the same pattern. It's going to be the cosine inverse of the numerator. Since gamma is the angle and gamma is opposite C, C shows up on the opposite side of the formula. So it's going to be a squared plus b squared minus c squared over 2ab. So remember, the opposite information, the c and the gamma, shows up on opposite sides of the formula. That's why I write this vertically instead of horizontally. Just so I could say that. Normally I write all my formulas all sideways and stuff, but now it's like, no, I need to do the opposite thing here. So on our calculating machines, we'll just type cosine inverse. I'm going to open up parentheses for the numerator. And that's going to be 894 squared plus 850 squared minus the 810 squared. Not so on opposite ends now. Close the numerator, divide, and then open up the denominator. And I have 2 times A times B. Now I can take this to the calculating machine. Second cosine for cosine inverse. Open the numerator, do 894 squared plus 850 squared minus 810 squared. Close the numerator, divide, open the denominator, 2 times 894 times 850, 50. Close the denominator, close the cosine inverse, double check. A, B, C, 2A, B, cosine inverse, we're in degrees, hit enter. Looks like gamma is 55.3 degrees. Now we have an abundance of information. We have more choices to make. Realistically, at this point, since we have a set of opposing information, we have side C and angle gamma. At this point, we would use the law of sines to find the next angle. But unfortunately for our heroes, I haven't told you what the law of sines is. But fortunately for our heroes, in this situation, we can still use the law of cosines. So at this point, we would use the law of sines to find our next angle. But I haven't told you what it is yet. So we can still use the law, we still have all three sides, and we can use that to find any of the angles. So but that's okay. Law of cosines is so much better. And you can believe that all the way up until I tell you what the law of sines is. But we could just rearrange this and say find angle beta. And that will be just the cosine inverse of a squared and c squared minus b squared divided by 2 times a times c. So trade our 850 for our 810. So it looks like angle beta is 59.6 degrees. Now, if we wanted to be extra, we could just use the law of cosines to solve for alpha, but that's crazy. Now we know two angles, we should subtract to find the third. So now we know two angles. So alpha is just 180 minus 55.3 minus 59.6. Forgot to mention in the last example, but we should do a reality check. Remember, the biggest angle will be opposite the biggest side, and the smallest angle will be opposite the smallest side. That leaves the middle angle to be opposite the middle side, but we don't mention that one. And I think that's just another extension of middle children being ignored. I wouldn't know. I'm an only child. That's why I'm so selfish. So the biggest angle, alpha, is 65.1, and that is opposite the biggest side of A at 894. The smallest angle is 55.3 degrees, which is gamma, and that's opposite C, which is 810. And so the smallest angle is opposite the smallest side. And that leaves the middle angle, 59.6, to be opposite the middle side, 850. So there you go, Jan. Any questions? So that raises the question, what's the law of sines and when do we use it? But I see in the chat, a much more important question. What car do I have? I currently drive a Subaru BRZ, limited with the manual. And it is a great car. If you're looking for a fun to drive car, I super recommend it. And I'm not just saying that because mine is going to be up for sale in the next few months. But if you're looking for a fun to drive car that's not really that expensive, I recommend it. My car before that was a Miata, 2003 Miata. So clearly I have a type when it comes to cars. Any non-car related questions, comments, snide remarks? All right. It would be really helpful if I told you what the law of sines was going into this weekend, so you would know how to solve or when to use the law of sines, how it's so useful when you finally get a set of opposite information or when you start off with a set of opposite information. And man, if I would only do that right now, it would make your trigonometric lives this weekend so much easier. And everything would just snap into place and life would be so simple. And like you're thinking, dude, isn't that literally your job to make our mathematical lives easier? And I say, no, it is not. It is to make your mathematical lives more difficult so that your future mathematical life is easier. So embrace the struggle. And you can be mad at me all weekend for not telling you about the law of sines. When you find out how easy the law of sines is to use in most scenarios, especially like this one, you can be extra mad at me. So that's going to do it for today. That's going to do it for this week. I'll see you all on Tuesday. Study up your law of sines. Have a good weekend. And thanks for playing.